All right, let's get right into it. Have you ever really thought about the invisible magic that keeps our digital lives in order? You know, from your massive music library to your social media feed, sorting things is one of the most basic jobs a computer does. Today, we're going to pull back the curtain on one of the slickest, most powerful ways to do it: merge sort.
Seriously, think about it. You tap in a new contact, and bam, it's right where it should be, alphabetically, in a list of maybe thousands of names. How on earth does that happen so fast? Well, I can tell you it's not by using some simple clunky method. That would take forever. The secret is a much, much cleverer approach.
And that really gets us to a core idea in computer science. See, on one side, you've got your simple sorts. They're easy to wrap your head around, but their performance, what we call O(n squared, gets painfully slow as your list grows. Like, if you double the items, it takes 4 times longer. Yikes. But on the other side, you have advanced sorts like merge sort. Their performance is what we call O(n log n, which is just ridiculously faster and makes sorting huge amounts of data actually possible. The secret to that speed? A truly brilliant strategy.
And that strategy is called divide and conquer. It's this powerful way of thinking that you see all over computer science. And honestly, merge sort is its poster child. It uses this idea perfectly.
The idea itself is actually super intuitive. You're faced with this huge, impossible-looking task, right? Well, don't try to tackle it all at once. Break it down. Chop it up into smaller, much easier pieces. Solve each of those little pieces on their own, and then, this is the key, you cleverly stitch those solutions back together to solve the original monster problem.
So it really all boils down to 2 main phases. First up is divide. In sorting, this just means we keep splitting our list in half, again and again and again, until we're just left with a bunch of tiny lists with only one item in them. And a list with one item? Well, it's already sorted, right? That's the easy part. Then comes the conquer phase, and this is all about merging those tiny sorted lists back together in a very specific and, frankly, genius way. And that brings us right to the heart of the algorithm. Look, the dividing part is easy. It's the conquer phase, that merge step where all the magic really happens. This is the one move that gives merge sort all its power. So the game plan is this. The algorithm keeps calling itself, first on the left half of the list, then on the right half, until everything is broken down into single pieces. Then on the way back up from all those calls, it does its signature move. It merges those now sorted halves. But, you know, how does that merge actually work?
All right, let's zoom right in and see how the gears turn. The setup is really important. Just imagine we have 2 lists, and because of all that recursive dividing and conquering, each one is already sorted on its own. Our only job now is to combine them into one big, perfectly sorted list.
Okay, here we go. We put a pointer at the start of each list, and we ask one simple question: which number is smaller? In this case, it's a contest between 2 and 1. The 1 wins, easy. So we pluck it out, put it in our new final list, and we scoot the pointer on the right list over 1 spot. And then we just do it again. The new comparison is between 2 and 9. Who's smaller? The 2, of course. So the 2 gets the next spot in our final list, and we move the pointer on the left list forward. See? It's just a simple game of pick the smaller one. Let's do one more just to lock it in. Our pointers are now looking at 7 and 9. 7 is smaller, no doubt about it. So it gets picked, moved over to the final list, and we advance the pointer on the left again. You see the pattern emerging, right? We just systematically pick the smallest element available every single time.
Now this picture shows the end game perfectly. This simple comparison process just keeps going until one of the lists is totally empty. At that point, what do? Well, we know for a fact that every number left in the other list is bigger than everything we've already moved. So we can just grab that entire leftover chunk and tack it onto the end of our result. So clean, so efficient.
So we've just seen how it all works. But now for the really satisfying bit. Understanding why this whole method is so blazingly fast. It's time to unlock that O(n log n secret.
Yeah, that's the million-dollar question, isn't it? That n log n thing, it looks a little mathy, a little intimidating. But trust me, the logic behind it is actually super visual, and it makes a ton of sense once you see it.
The absolute best way to picture the work being done here is to imagine a tree. Every time we split the list in half, we're basically creating a new level of branches in this tree. At the very top, you have the original, unsorted list, and at the very bottom, on all the leaves, you have the individual elements.
And here's how we piece together that n log n. The log n part, that comes from the height of the tree.
I mean, if you have n items and you keep cutting that number in half, it only takes about log base 2 of n cuts to get down to 1. That's the number of levels. Then you've got the n part. At every single level of that tree, if you add up all the little merge operations happening, you have to look at all n items. It's a full sweep. So let's put it together. You're doing n units of work per level, and you have log n levels. You multiply them, and you get n times log n. That's the secret sauce.
But of course, no algorithm is a silver bullet. It's not perfect for every single job. Like any professional tool in a toolbox, merge sort has its own specific pros and cons, and it's really important to know what they are.
This little table lays it all out. Its time complexity is its superstar feature, right? A guaranteed O n log n. It doesn't matter if the data is a total mess to begin with, it's always fast. But here's the trade-off. Its space complexity is O n. That means it needs extra memory to work. And finally, it has this great property called stability. Let's just quickly break down what those last two things really mean.
First, what does in place mean? Well, an in-place sort is an algorithm that can get the job done by just shuffling elements around inside the original list without needing a bunch of extra space. Because our merge step needs that temporary array to build the final list, merge sort is not an in-place algorithm, and that right there is its main drawback.
Okay, and what about stable? This is a really cool property. A stable sort promises that if you have items with the same value, they'll stay in the same order relative to each other after the sort is done. So imagine you sort a list of people by city, and then you sort that same list by their last name. A stable sort makes sure all the people from, say, Chicago are still in the same order they were before. This is a huge advantage in some cases, and merge sort has it.
So what's the big takeaway here? Why does this all matter? Well, merge sort's guaranteed speed makes it a rock-solid choice when you're dealing with huge datasets and you just can't afford a slowdown. Its stability is an absolute game-changer for complex, multi-level sorting jobs. And this isn't just some academic idea. It's so good that it's a key ingredient in super optimized sorting algorithms that you use every single day, like the stable sort function in C++ or as part of Python's timsort.
When you get right down to it, merge sort teaches us something that goes way beyond just code. It's this beautiful example of how, sometimes, the best way to solve an overwhelming problem isn't to just charge at it head-on. It's to have the wisdom to break it down into tiny, simple pieces you know you can solve, and then build your solution up from there. So it kind of leaves you with a question, right? What big problem in your life could you conquer by applying a little divide and conquer?